So when it comes to the geometric series, the first thing that you want to understand is the layout of that sequence. So how does it look like, and how do we actually deal with questions to do with this type of sequence? So when it comes to this, of course, you always want to look out for the sum. So it has a coefficient. A here is a coefficient, and then after that you have something like an r, so an r term, and then this term is raised to some power, and the power here is our n, where n is changing from when n is 0. So this one will start from n is 0, and then it goes all the way up to infinity. Okay, so let me just make sure we're recording this. Okay, yeah, we are. Okay, so this one starts from n is equals to 0, and it goes all the way up to n is equals to infinity. So this is how the geometric series is going to look like. Now, what we want to see here is, firstly, what does this notation mean? After we understand what the notation means, the next part will be to look at when does this converge and when does this expressions of this nature, when do they diverge? So if you have an expression that looks like this, what it just represents, or what it means here, is that for different values of n, starting from when n is equals to 0, and this being a summation, so it now means that this summation from n is equals to 0 all the way up to infinity, and then you have a r to the power n. When n is 0, you're going to end up with a r to the power 0, and r to the power 0 is the same as just 1. So that will reduce to just 1. So the whole term here is just going to remain as a. Then the second term is going to be plus a r to the power 1. So here, n is equals to 0. Here, n is equals to 1. And then, and so on and so forth. So if we were to just write the first few terms of that sequence, how would they look like? So let's write the first few terms. So n is equals to 1, we have this. I'll just write it without the n there. Then the next part, we have a. Then this is going to be r to the power 2. And then we have a here, r to the power 3. And then a r to the power 4, plus, and so on. Okay, someone trying to join us. Okay, so this is the sequence that we are looking at. Now, when you look at this expression, it will keep on going until when n approaches infinity. Now, what do we want to look out for here? Well, firstly, or more importantly, when it comes to expressions like this, for you to determine whether this expression converges or not, you want to look at that value for r. The value of r is going to be the key term when it comes to convergency of this expression. Now, how will it work? Well, in this case, you want to look at the value for r, the value that is going to be down here. A here, of course, is a value. It's a constant as well, but you want to look for the argument of that exponential term. So if r here is greater or equals to 1, so if r is greater or equals to 1, what this is going to mean is that this geometric series is going to diverge. And if the value of r there is in the range from 0 up to 1, without including 0 and without including 1, then the conclusion here is going to be that the expression converges. So good examples here would be the ones that you guys did in class, where you had something like, let's say you have the sum to infinity from n is equals to 0. And then you have, we can just pick random expressions here. Let's say you have, the one I like the most is, I think this one where you had a 2 here. I think it was a 3. 3, and then you had 2 to the power n. Now, if this is a geometric series, it means that we must write it somehow in this form, where you have a constant number here, a, and then multiplied by a term raised to the power n. So you always want to identify which term is going to be raised to the power n. And in this case, you can see that the 2 there is raised to the power n. meaning that the 3 is the constant there. So you have n is equals to 0, and then you have infinity there. The 2 separately, this is going to be, 3 separately is going to be 1 over 2n. When you look at this expression, this is what has to represent your r. But when you look at it like this, we want it to look in this form, not the r being down here, as in like that. R here has to be a whole thing, not in the denominator. So how do you get that? Luckily for us, the numerator is a 1. So because the numerator is a 1, we can obviously rewrite this expression so that we now view it as 3 multiplying the whole thing 1 over 2. So that the whole thing now is raised to the power n. So when you look at this now, we can easily argue that the 3 here represents our a, and the 1 over 2 here represents our r. So that we can now look at what that r term is. R is equals to 1 over 2. So if the question is to determine whether this series converges or diverges, all we have to do now is analyze the value of r. To converge, we know to say r has to be in the range from 0 all the way up to 1 without including 0 and 1. In this case, our r is half. Clearly, half is within this range, so we can argue that this sequence converges. Any questions there? Okay, so
excuse me, sir.
Yes, please.
Yes. 1 over 2 to the power n. Why did we take it take the 2 up, then the n you say minus n on top of it?
Okay, so let's see what you're saying there. So what you're saying there is we have this, and then we have this is a, and then this is sorry, this is not a, this is 3, and then we have 1 over 2 to the power n. Okay, now what you're asking here is, why didn't we rewrite this and say this would be the same as n is equals to 0, and then 3, and then we have 2 to the power minus n? That is the question, right?
Yes, sir.
Okay. Who can answer this? Anyone to try it? No, we can't say it diverges. It's the same expression. So we should still go back to the conclusion that it converges. Now,
Can I try?
Yeah, please go ahead.
It's because from the summation there it says n should it's starting from n equal to 0 up to infinity, meaning must be positive, and n mustn't be negative.
Okay. That's something, but the summation actually doesn't affect where n starts here from here. The negative here is separate from the n there. So yes, you do have a point there, but it's just not the way you've expressed it. Yeah. Do we have any takers? It's similar to what the last student actually mentioned there. Ideally, the reason why we don't take this route, this is still mathematically okay, but the problem here is that we want to represent this such that you have an a term here and you have an r term raised to n. Now, the difference here is you see the power here. it's not negative n, it's positive n. But doing this leads you into having a negative n. We want the power to be positive n, not negative n. Have you got that?
Okay. Yes, I've seen it.
Yeah. So because we want to have that positive n and not the negative n, we will not take this route. In fact, if we take this route, we'll be forced in an attempt to get rid of that negative immediately in the next step. We will have to come back and say, take it back down so that it gets to be a positive. And then once it is like this, you'd have to observe that then this is what ends up giving you this. Now this works to that standard where we have a here multiplying r term raised to positive n there. Does that make sense?
Yes, it does. The understanding was that maybe n can be any number. I think that's why I was lost.
No. The power of the r term there is, as now we can even use what was given to us earlier on. The power of that n power, or the power of the r term. The power of the r term is going to change from n is equals to 0 to n is equals to infinity. So if you have it in this form and redefine it so that now you have a, maybe r to the power, let's say some new power k, where k is equals to negative n, you now see that the power here, the values of k are now going to be negative, which now is not okay. This is no longer the geometric series. Have you got that?
Yes, sir.
Okay. Let's see if we can find a few examples that actually use this this series. Let's see if we can find a few from here. And we have any random examples that they've placed here. This goes to 1 to that. Can you guys identify anything interesting that we can use? How do you think about this one here? Does this conform to the geometric series? No, I think it doesn't, because n here is also going to be changing.
Your screen is not showing.
Okay. So when you look at question 3a here, quite tricky really. What are they saying? They're saying you have the sum of a series. The first one is a, first term is a, then you have ar there, then you have plus, you keep going up to a r minus, as in n minus 1, as the last term, where r is not equal to 1. Here they're saying that r is not equals to 1. They want us to show that this sum will be equals to a, and then we have r to the power n minus 1 over r minus 1. Now this part to say r cannot be equals to 1, notice that it's brought about because of this denominator here. Since we're saying the denominator there is going to collapse if the value of r is actually a 1 there. Okay, and you have to see that this is more like a geometric series here, because if you look at this, the first term is ar to the power 0, and the second term is ar to the power 1. The third term, you obviously are going to get ar to the power 2, plus, and so on. Now they're saying that if we only go up to ar to the power n minus 1, just up to minus 1, then the whole thing can reduce to just this expression. So you can define you can define what the last value there is. We can control to say that, okay, maybe we just want to go up to 10, up to n is equals to 10. So it implies that the last term here will have to be r to the power 10 minus 1. So this will just have to go up to r to the power 9. So this is what this sum is all about. So it's just the first few terms of that geometric series. Now, how do we prove that this identity holds? So let's go right ahead and see the math for it. For this example, we want to prove that the sum of the first n terms of a geometric series is equal to a, and then r to the power n minus 1 over r minus 1. So this, of course, is for r not equals to 1. Now, how do we do it? Well, let's try to expand this series a little bit first. So if we wanted to get the first few terms, what we'd have to do is that sum is going to be equals to the first part when n is equals to 1. We know to say we're just expanding this from n is equals to 0 up to n, whatever our n is, of a r to the power n. So to expand this, first r is equals to 0. So this is just going to be a plus the next part, r is equals to, not r, I mean, n is equals to 0. We get this. Next, r is equals to, I keep saying r, sorry for that. For the second term, n is equals to 1. So you get a r to the power 1. For the third term, n is equals to 2. We get a r to the power 2. And for the third term, n is equals to 4. So we get a r to the power 4. We know this behavior is going to continue to keep going up to, let me do this, move this a little bit. We know to say this will continue. The last term has to be n just one less. You know, n is the number of terms. First term, second term, third term, fourth term. The last one here, first, second from last, is going to be a r to the power n minus 2 and plus, then the last one is going to be a r to the power n minus 1. That is going to be the last term. So if, let's say, you were dealing with the first 7 terms, n is equals to 7. So for the first 7 terms, you're going to have 0 here, 1, 2. Yeah, that's n is equals to 0, n is equals to 1, n is equals to 2. I skipped n is equals to 3 here, sorry for that. From n is equals to, so that's power 1, power 2, power 3 next, then power 4, 5. Now, what does this mean? The last term in this expansion will have to be 7 minus 1. So this will have to be power 6. And the second from last will have to be 7 minus 2. It will have to be r to the power 5. This will be the second last term. So I hope that makes sense. Now, after expanding it in this, of course, in this case, we're keeping it general so that, yeah, we can use this for anything really. So keeping it general. Once you reach this part, multiply each term by r. So when you multiply each term by r, look at what you're going to get. This is going to be r, and then you're going to have Sn here. And then how about everything else that will follow on the right side? A times r is going to be ar, plus ar here times r is going to be ar squared, plus then this is going to be ar to the power 3, plus this is going to be ar to the power 4, plus everything is going to continue in this way. By the time you multiply this by r, it's going to be ar to the power n minus 2, but you're multiplying it by r, just a single r, which is to the power 1. So r to the power n minus 2 times r to the power 1 is the same base, so you know you're going to add the powers. So when you add the powers here, this is just going to be what? It's going to just be r to the power what? This will reduce to power what? Can you see that?
N minus 1.
Yeah, so this is now going to be to the power n minus 1. So the second last term now is going to be r to the power n minus 1, plus, if I do the same thing to the last term, what do you reckon that will become now? What will be the last term now? If you multiplied it by R as well.
It will just be A.
It will just be, what?
So it will be AR to the power N.
Yes. That term will now be A R to the power N, because you're going to have A R to the power N minus 1 multiplying R to the power 1. When you add the powers, it will reduce to just A R to the power N. So once that is done, let's label the first equation as equation 1, the original one. And let's label this. Yes, please.
Why are we multiplying everything by R again? I've forgotten where you said that.
We just want to shift it once so that we can more like subtract these and see what will remain. It's more like a trick to just getting the answer. You get that?
Okay.
Yeah, it's just a trick that we're using here. So what we're going to do at this point, we are now going to subtract these two equations. Clearly, equation 2 is a little bit bigger than equation 1. It's a little bit more. So we're going to subtract from equation 2, we'll subtract equation 1. Now, how will this happen? On the left side, notice that we're just going to have, on the left-hand side, we're going to have from equation 2, R Sn minus Sn. This will be on the left side. How about on the right side? On the right side, notice that to subtract, terms will have to be similar. By similar, let me say corresponding. By corresponding, they must have the same power, meaning this with A R will subtract with this. It will literally die out. This with A R squared will subtract with this term. This with A R to the power 3 will subtract with this. And the one with A R to the power 4 will of course have something to subtract with. But notice that the last term to subtract is going to be A R to the power N minus 1, which will subtract with the last term in equation 1. The terms that will survive from equation 2, it's going to be this term here. So from equation 2, what will remain is going to be A R to the power N, because there will be nothing in equation 1 that will go up to A R to the power N. But in equation 1, one term will remain. Can you guys see which term? What term will remain in equation 1?
A.
A. You have to see that even though I haven't crossed this one out, it will have its counterpart just before this one that it is going to cancel out with. The only term that will not have anything to cancel with in equation 1 is going to be the A here. So it will subtract, but it will have nothing to match with, or it will have no like term to subtract with. So it will remain there. So we're going to reach here after subtracting equation 1 from equation 2. From here, we can then try to simplify this. If I factor out Sn from the left side, I'll end up with Sn. Then I'll have R minus 1 equal to, on the right side, I have A R to the power N minus A. When I divide both sides by R minus 1, notice that now I end up with Sn equal to A R to the power N minus A over R minus 1 as the sum. Now, is this the expression that we wanted to get? Look at that. It is the one. To make it really look like the one, all we have to do is factor out A. So that the sum now becomes A coming out, R to the power N minus 1 divided by R minus 1. Of course, again, for R not equals to 1. So we have proved the identity. You see, because of the tricks that are involved in certain calculations or certain steps, it's why I always say that if you've never seen something being done before, there's a good chance that you won't be able to do it. So the more questions you work out, the more you'll be capable or the more comfortable you get in terms of working out any question that you find, because it will show you just so many different ways of approaching these questions. Because I'm telling you, if you had not seen that trick of multiplying with R, you would not see the reason to do it in the first place. You would not do it. I know I wouldn't do that if I had not seen that before. Any questions here?
Are there any other tricks we can use?
For this one? For this one, no.
Oh, okay.
Yeah, maybe if you try to expand it, set n to be 1, try that, set. Yeah, maybe you should try trial and error. It can also work. But this is the easiest and quickest way to do it.
Okay. Can you kindly scroll up?
Up to where?
Just down.
Here?
No, the opposite direction. No, down. Again. Again. Okay, just there. Just there. Thank you.
Okay.
Sorry.
Okay, so we have proved that expression. Now, this, as I mentioned earlier on, this is what you would use if you were asked to say, you're given a geometric series. Let's say you have like the one that we looked at earlier on, where you have, this is going up to, let's say up to n. Of course, we know it's usually it's n up to infinity, but let's say up to n, from n is equals to 0. Then you have AR here to the power n. So if they wanted you to find the first few terms, like let's say if this such a sequence was, let's say, up to n, and then you have like what we had earlier on. And then this is, you can even do the second part. Like I think we had 3 to the power 2, and then to the power n. So if you look at something like this one, clearly you can tell what is going to be your A in this case.
One.
And your R?
3/2.
3/2. So here, our A is equals to 1, and our R is equals to 3/2. Okay, have we pointed out when a geometric series converges and when it doesn't? Yes, we have. When R is in the range from 0 to 1, without including 0 and 1, we know it converges. But when R is greater or equals to 1, then we know the series diverges. So when you look at this expression, does it converge? Does it diverge?
It diverges.
So this one, the conclusion will be that it diverges. But what if we wanted to find, let's say, the first 5 terms? What if we wanted to find the first 5 terms of this sequence? How would we approach it? See, according to the identity that we've just derived, all you need is A, R, and the number of terms you're interested in. So our A here is 1. So first we have A. This is R to the power n minus 1 over R minus 1. Here, of course, R must not be equals to 1. And clearly in this case, you can see that R is not equals to 1. Because of that, this test can actually work, or this can work. So when we do this, our A is 1, our R is 3/2. Now it is to the power n, our n is 5, so this is the first 5 terms, minus 1, and then divided by our R again, which is 3/2, then minus 1. So simplify this, and whatever you get will be the sum of the first 5 terms. Now, if you had to do this manually, it would take you a little bit longer. Of course, here maybe for 5, you might say that you can pull it off. But imagine if you are getting the first 20 terms, or you are working it out for, let's say, some up to maybe even 50. You see that there it is going to be a little bit more complicated. Now, I have a question for you guys. You see, for that identity to work, we keep saying that R must not be equals to 1. Okay, yeah, R must not be equals to 1. Okay, I think there's really not much there. What I wanted to point out, or what I wanted to ask was, if R was equals to 1, not R. I actually wanted to look at when n is 1, but then that doesn't make sense. I think what I want to ask is for the series that we want to examine next, which is the P series. And the harmonic series.